This video was brought to you by GeneralPack.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/generalpack. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies. Introduction to Relays Part 1B. This is the second part of the series of types of protective relays and design requirements. In this part, we will have a discussion on the factors that need to be considered when designing a relay-based protection system. The purpose of protective relaying system is to rapidly remove any of the components of the power system when they start to operate in an abnormal way, and to do this effectively and accurately. A protective relay scheme should be designed by considering the following factors, and we could refer to them as the relay design requirements, similar to most textbooks and technical papers. These design requirements are selectivity, reliability, speed, sensitivity, simplicity, and economy. So the first one is selectivity. A well-designed and efficient relay should be selective. For example, it should be able to detect the point at which the fault occurs and causes the circuit breaker that is closest to the fault to trip first. So let's suppose that we have a fault near point 3 as shown in the diagram, and we have breakers and relays placed at several locations in the network which are marked by numbers. So which of these breakers should trip for a fault near point 3? In this case, relay number 3 and 5 should trip first as opposed to 1 or 4 or 7. Now if that happens, we know that the relay protection scheme is selective, which means it causes the closest relay to trip without disturbing the remaining system, so that the fault is cleared with a minimum system outage. Now we move on to the next one, which is reliability. A relaying system should be reliable, which means that the system should not operate unnecessarily. Without reliability, a protection would be rendered largely ineffective and could even become a liability. Now let's suppose that generator 1 was running and circuit breaker number 3 closed to synchronize with the grid. But immediately after closing, it tripped because high current flowed due to the energization of the transformer, and if that happens, the scheme is not reliable. That is just one example of reliability. There are multiple examples that can be given. Number 3 is sensitivity. Sensitivity is the ability of the relay system to be sensitive enough to detect even a small amount of fault current. It means that the relay is able to sense and respond to a minimal change in the measured parameters, and current is the most common measured parameter. For example, let's suppose the insulation damage on an underground cable linked after breaker number 14 causes current leakage. A sensitive relay should detect the current leakage, which may eventually turn into a ground fault. If a protection system is able to detect a small abnormality, then it is sensitive enough to function properly. Number 4 is speed. Speed is to maximize safety and minimize equipment damage and system instability. A fault should be cleared as rapidly as possible. This indicates that the relay should quickly attain a decision, and the circuit breaker operation should be fast enough to isolate a fault. If the relay is able to disconnect the faulty system as fast as possible, equipment damage that may result from flow of heavy fault current can be prevented, and further escalation of faults can also be prevented. Looking back at our previous network, let's suppose we have a fault in the transformer winding. Relay 3 and 4 must be able to quickly disconnect the system before the transformer catches fire and destroys itself completely. The next one is simplicity. The relaying system should be made simple so that it can easily be engineered and maintained. Reliability is closest related to simplicity. Generally speaking, the simpler the protection system, the greater the reliability. A simple system is probably the one which causes the least amount of relays to give optimal protection. And the final one is economy. The most significant factor of a particular protection system is the economy. Sometimes it is economically unjustified to use ideal schemes of protection that protects all elements of the system with full reliability, and a compromise method has to be adopted. In our network, we have a total of 15 relays that protect the system. However, it will be costly to install and maintain all 15 relays. Hence, the choice is to be made. We could easily remove relay number 9 in favor of a tie switch, and to minimize the cost without compromising a protection reliability. Else, relays 7 and 8 could be replaced with more advanced relays so that the need of relays at point number 5 and 6 is eliminated. It is a core job of the design engineer to reach an optimum point of trade-off between cost and reliability. However, when the apparatus to be protected is utmost important, example like a generator or a main transmission line, economic considerations are generally subordinated to reliability. That is all for this part of the series. Now in the next part of this video, we will be discussing the most common different types of relays that is used in electrical power systems, their mechanisms, and their applications as well. Now we hope you have a continued interest in this topic and series as either a student or a professional, and we hope you find this content useful and enlightening. Please consider subscribing to GeneralPack.com and becoming our patron at patreon.com/GeneralPack. GeneralPack.com, making power systems intuitive, open, and free to everyone, everywhere. Thank you.